The examples in this section go with lesson 7.4, vectors. This is part 1. Example 1, vector v extends from the point 0, 0 to the point positive 3, positive 4. Vector w extends from the point negative 2, positive 3 to the point negative 5, negative 1. Part A, find the magnitude of v and the magnitude of w. Okay, for part A, the magnitude of v is just the distance formula. Essentially, we just want to know how long this is. So we're going to do x2 minus x1 squared plus y2 minus y1 squared. And if we put all this into the calculator at the same time, we're going to end up with the square root of 25, which we know to be 5. So v has a nice magnitude because 25 has a nice square root to it. Now w, we're going to do the same thing. This is another distance formula problem. And we are going to take x2 minus x1, and we're going to square that, and we're going to add it to x2 minus x1, and we're going to square that. And we're going to put all this into the calculator at one time. And this is also going to give us the square root of 25, which is equal to 5. So right now what we know is that vector v and vector w have the same magnitude. Now part B is asking me, are the two vectors equal to each other? Well, that's half the battle. They have the same magnitude. But if they're going to be equal, they also have to be going in the same direction. And in order to figure that out, we should probably draw a picture. And if they're heading in the same direction, then yes, we can say that we have equal vectors. All right, 0, 0 will be right here. Positive 3, positive 4, right there. And this word 2 right here tells me that the endpoint is going to be at 0, 0, and then the vector is going to end right there at 3, 4. Our other one is at negative 2 and positive 3. This is going to be our endpoint because there's the magic word 2 there. And at negative 5, negative 1, that's where my endpoint is going to go. And so we can say that no, these vectors are not equal. And the reason they're not equal is because they're not going in the same direction. Vector w is going down toward quadrant 3, and vector v is going off into quadrant 1 there. Example 2, suppose the vector v has initial point negative 4, positive 5, and terminal point negative 1, positive 12. Part A, find the component form of v. All right, our formula for the component form is just going to be x2 minus x1, comma, y2 minus y1. So let's see if we can find the component form of this. Let's see, we're going to have negative 1 minus negative 4, comma, 12 minus 5. And if we simplify this, negative 1 minus negative 4, these negatives are going to cancel. That's going to leave me with a 3. And then 12 minus 5 is going to leave me with a 7. So our component form right here, positive 3, positive 7. Now, part B, if we place the initial point at negative 2 and negative 4, what's the terminal point of V? Okay. Well, since we already know the component form of the vector, the terminal point is going to be located at the x-coordinate of the initial point plus the first component in your vector, comma, the y-coordinate of your initial point, plus the second part of the component of the vector right in there. And so that means our terminal point will happen at +1 and +3. Example 3, given that r is equal to the vector -3, +10, and s is equal to the vector +12, -7, find part A, r plus s, and part B, s minus r. Well, r plus s is just going to be the vector that adds each of the parts of this component form. That means we're going to add -3 plus 12. They're the first parts of the component, and then I'm going to add 10 plus that -7. They're the second parts of the component form. And this is going to give me the vector +9, +3. Now, if I want to subtract these two, this is s minus r. That means I'm going to do the s components minus the r components, but I'm still going to subtract the first minus the first and the second minus the second. So we're going to look at 12 minus a -3, comma, -7 minus 10. And when we simplify this, I'm going to get +15 and -17. Example 4, given vector A is equal to +11, -7, and vector B is equal to -4, -6, find part A, 6 times A, and part B, -3 times A plus 10 times B. In order to do 6 times A, we're just going to take the scalar 6, and we are going to multiply it by vector A, which is +11, -7. And now we're going to treat this kind of like the distributive property, because I'm going to multiply 6 times 11 and 6 times 7. And this is going to give me the vector 66, -42. And that's it. We now have 6 times A. For part B, we're going to kind of do the same thing, but you'll notice I'm multiplying something by A vector and something by the B vector. So this is going to be a little bit longer. But essentially, we're going to take -3 and multiply it by the vector A here. And then we're going to add that to to 10 multiplied by the B vector here. Now I'm going to use my distributive property here to get a new vector, -33, +21. And then I'm going to use my distributive property here to get a new vector, -40, -60. And then I'm supposed to be adding these two vectors together. So -33 plus -40 is -73. And then 21 plus -60 is going to give me -39. So it looks like that is my -3a plus 10b. Example 5, find a unit vector in the direction of v is equal to the vector +5, -1. All right, the unit vector, that just means that when we square these components and add them together and square root it, we're going to get 1 out of it. Okay, the way to make sure that we have a unit vector, first thing we want to do is we would like to find the magnitude of our vector. So let's do that using the distance formula. We'll have 5 squared plus -1 squared. This is going to give me the square root of 26. Does not have a nice square root here, so we'll have to leave that as it is. Now, the unit vector is just my vector divided by its magnitude. So essentially, I'm going to have 1 over the square root of 26 times the vector v, +5, -1. And that's going to give me the vector positive 5 over the square root of 26, comma, negative 1 over the square root of 26. And since we don't leave radicals in the denominator, we will need to rationalize these. It will become the vector positive 5 times the square root of 26 over 26, comma, negative square root of 26 over 26. And if you forgot how to rationalize, remember we did it this way. We had 5 over the square root of 26 times the square root of 26 over the square root of 26, which gives me 5 times the square root of 26 over the square root of 26 squared. But remember, they're just going to cancel out, so we're left with 5 square root of 26 over 26. And that's where this first number came from. And the second one came from something just like that. We took negative 1 over the square root of 26. We want to get that radical out of the denominator, so we multiply by the square root of 26, top and bottom. This is going to give me negative 1 times the square root of 26 over the square root of 26 squared. But remember, they're going to cancel out, so we're going to be left with negative square root of 26 over 26, or negative 1 times that, either one. But in any case, here is our unit vector. Example 6, part A, write the vector positive 12, negative 1 in terms of I and j. Well, this one's not too horrible. This is already in component form, and so if I want to write this in terms of its horizontal and vertical components, I'm just going to write this as 12i minus 1j. And now it is written in terms of I and j. For part B, we're given the vector negative 9.4i plus 7.1j and the vector v negative 0.6i plus 3.2j, and we're supposed to write negative 2a minus 4b in terms of I and j. Y'all, this is almost going to be like adding your like terms kind of a situation. All right, so negative 2a minus 4b is going to be negative 2 times 9.4i plus 7.1j minus 4 times negative 0.6i plus 3.2j. Now let's distribute into the parentheses here. Let's see, 2 times 4 is 8, 2 times 9 is 18. So we have 18.8i. That should be minus. Because we have negative 2 times a positive 7, so it's going to be minus 14.2j. All right, over here, negative 4 times negative 0.6, that's going to give me positive 2.4i. And negative 4 times positive 3.2, this is going to give me negative 12.8j. And finally, all we need to do is add our like terms. So let's see, 18.8 plus 2.4, that's going to give me 21.2i. And then we have 14.2 minus 12.8. They're both negative, so let's add them together. This is going to be negative 26, negative 27.0j. And here it is in horizontal and vertical component form. Example 7. A man exerts a force of 80 pounds on an object by pulling on a rope at an angle of 30 degrees from the horizontal. Write the force vector F in terms of I and j. Okay, things that we know. First of all, we know that the magnitude of our vector is 80 pounds. And we know that our angle is going to be 30 degrees. So our force vector should be 80 times the cosine of 30 degrees, comma, 80 times the sine of 30 degrees. Let's see. The cosine at 30 degrees is square root of 3 over 2. And the sine at 30 degrees is 1/2. All right, over here we're going to have 80 times the square root of 3 over 2. But this fraction right here reduces. That actually reduces to 40 times the square root of 3. And over here, 80 times 1/2 is just 40. And if we want to convert this back into I and j form, then we're going to have 40 times I square root of 3 plus 40 times j. And there's our force vector.